Okay, so I will talk about GNSS and more specifically GNSS interference today. So I'm aware it's not the kind of topic which is usually covered here at Interop. So I'll try to stay high level and give you an example so that maybe you can relate to it. So I'll start by giving you like an overview of the GNSS market today and discuss the threats to these systems and more specifically so the interference threats. And then I will show how to mitigate these threats, this risk, and finally show you this with an example of a telecommunications network. Okay, so today there are four different GNSS today, sorry. So GPS is the most known, so this is the US government one, and then we have GLONASS, which is a Russian one, Galileo, the European one, and Baidu, the Chinese one. Today there are almost 4 billion GNSS devices used worldwide, so I think this figure is a bit outdated, it's a bit more. It's about 6 billion, so it's almost as many people on Earth. And the reason behind this is because this is driven by the smartphone market. So every day, today, most of the chipset manufacturers like Qualcomm or Broadcom, LTE or 3G chipset also have a GNSS receiver inside. And so we'll keep seeing this growing, and especially because GNSS is a support to all the major innovation that we see today. So for example, IoT, smart cities, connected autonomous vehicles. So all of this technology are supported by GNSS. For example, any IoT device that has a position sensor will use GPS as the first source for this sensor, for position information. Of course, another place where we see GPS is drones. So for courier delivery, for search and rescue, for surveying, for example, and drones also used as a primary source of position GPS. And finally, a bit less known, but GNSS is also the first source of timing information on Earth. So it's also used for timing, for accurate timing. And it's not only used in consumer technologies, but also in critical infrastructure. So, for example, power grids will use GPS timing for synchronization. I think it's about 1 microsecond accuracy needed. Transport, of course, transport infrastructure, but also financial markets. So ATMs or any financial transaction is use GPS for timestamp these transactions. And of course, we'll see that a bit later, but all the communications use GPS for timing. All right, so GNSS is very used, very common today, but it's not that robust. It's not a robust technology. Why? Because the GPS signals come from satellites, for example, at 20,000 kilometers, and when they arrive on Earth, they are very low powered, so very subject to threat like interference, for example. So today we have categorized the GNSS threat in 6 different categories. The first one being spoofing. So spoofing is when transmitter will emit a fake GPS signal and a receiver will be fooled believing it's in false position. Multipath is, for example, when you are in Tokyo city center, you use your Google Maps and you see the blue dot is moving. So that's because multipath. That's because you don't have a direct line of sight between your phone and the satellites, and the signal you actually received has been reflected on buildings, for example. Then we have interference. So interference could be intentional, like jamming. I will talk about that later, or unintentional. So interference coming from defective antennas around the receiver, for example. And we have cyber attacks. So cyber attacks is when the software layer of a receiver is hacked. That's also on the rise, mainly because of IoT devices, so connected devices that use GNSS. Then we have GNSS segment errors, which is when the control grounds, the monitoring ground of GNSS will upload wrong data to the satellites, and then the satellites will broadcast this wrong data to receivers. And finally, atmosphere, so that could be ionospheric scintillation, for example. So the sun will, there's like solar flares from the sun, and this has an impact on the ionosphere. And when the GPS signals go through the ionosphere, they are diffracted or refracted, and that introduces a delay in the signal.